So dear students, so today's class is solutions. So you know something about the basic ideas about solutions which you have learned in your previous classes. Solutions means anything, a homogeneous mixture of two or more substances in which the composition remains same throughout the mixture. So homogeneous mixture of two or more compounds or substances where the composition remains same throughout the mixture is commonly known as solutions. And normally we used to use a liquid as a solvent which is taken in large quantity, which serves as a solvent, and the one which is going to dissolve in the solvent in limited quantity is considered as a solvent. So depend upon the physical state, we have different types of solutions. Normally when we use a liquid as a solvent, we can dissolve either a gas in liquid, it is one type of solution. We can also dissolve a liquid in a liquid, it is another type of solution. We can also dissolve a solid in a liquid, it is another type of solution. Therefore, depend upon the physical state of the solute and solvent, we have different types of solutions. And today's our discussion is normally confined to a solution of liquid in liquid. A solvent is a liquid and a solute is also a liquid. And a liquid, a solution which is composed of, which consists of only two components or only two liquids is commonly known as binary solution. As the name itself indicates, any solution which consists of only two liquids is commonly known as, or two components is known as a binary solution. The one which contains three components is known as ternary solution, and the one which is having four components is known as quaternary solution. Normally, according to our topic and syllabus, we used to discuss only the binary solutions which consists of only two components. So, binary solutions, as we learned, which is composed of only two components, are of different types. There are different types of binary solution. So when we prepare a solution by dissolving two liquids where a solute is also a liquid and a solvent is also a liquid, such binary solutions are of three types. So there are three types of binary solutions. They are completely miscible liquids, partially miscible liquids, and completely immiscible liquids. So completely miscible liquids are those in which the two liquids are miscible with each other in all proportion at all temperature. For example, ethyl alcohol and water is a best and simple example for completely miscible liquids. And partially miscible liquids are those in which they are miscible with each other only to some extent at one particular temperature. Of course, their mutual solubility depends on temperature. Such liquids are called partially miscible liquids. Examples are phenol and water, triethylamine and water, nicotine and water. These are a few examples of partially miscible liquid types. And completely immiscible liquids, the two liquids which are not miscible with each other at any proportion are called as completely immiscible liquids. Benzene and water, toluene and water are common examples of completely immiscible liquids. Coming to the completely miscible liquids, in case of completely miscible liquids, remember we used to study the completely miscible liquid by applying Raoult's law. So, before going to Raoult's law, so I hope you know something about the basic ideas of mole fraction. Remember, when we have a binary liquid mixture which consists of two liquids, liquid A and liquid B, the solution consists of both A as well as B, and there is a mole fraction of A and there is a mole fraction of B also. What the Raoult's law says, remember, the ratio of the at constant temperature, the partial pressure of a component in the vapor state is directly proportional to mole fraction of the component in the solution. I mean to say this, when we have a liquid mixture which consists of both liquid A and liquid B, In the vapor state, we have vapors of A and vapors of B. Remember? So, both vapors of A and vapors of B, they create the total vapor pressure. In the total vapor pressure, there is a partial pressure of A and there is a partial pressure of B also. And the partial pressure of one component in the vapor state is directly proportional to mole fraction of the component in the solution. This is what your Raoult's law says. So mathematically, we have Raoult's law. The partial pressure of a component is directly proportional to mole fraction of the component A in the solution. And we have PA is equal to P naught A into XA, where PA is the partial pressure of the component A in the vapor state, P naught A is the vapor pressure of the pure component A, and XA is the mole fraction of the component A in the solution. Similarly, we have PB, B is the another component which is present in the solution. The partial pressure of the component B in the solution is equal to P naught B into XB, where P naught B, PB is the partial pressure of the component B, P naught B is the vapor pressure of the pure component B, and XB is the mole fraction of the component B in the solution. Then P total, then total vapor pressure is equal to PA plus PB. So I mean to say, the partial pressure of the component A in the vapor state and the partial pressure of the component B in the vapor state, the sum of these two will give you the total vapor pressure. This is what your Raoult's law says. Raoult's law can be defined in a very simple manner. In a binary liquid mixture at constant temperature, the partial pressure of each component in the vapor state is directly proportional to mole fraction of the component in the solution. If one particular component is more in the solution, its partial pressure will also be more in the vapor state. Then, in a binary liquid mixture, remember, all binary liquid mixtures do not obey Raoult's law. Most of the solutions, they deviate from Raoult's law. So, in order to obey Raoult's law, suppose when we mix the two liquids A and B, remember, we used to say this binary liquid mixture obeys Raoult's law only when the attractive force between A and A and the attractive force between B and B. Remember, when they mix together, there will be an attractive force between A and B. Remember, the attractive force between A and B should remain same when compared to the attractive forces between A and B and B. Then only that binary liquid mixture obeys Raoult's law. In case, if the attractive force between A and B is either more or less when compared to the attractive forces between A and B and B, such solutions, they do not obey Raoult's law, they deviate from Raoult's law. So when any binary liquid mixture deviates from Raoult's law, there are two types of deviation, positive deviation and negative deviation. Then, which one is called as positive deviation? Remember, we used to say that a binary liquid mixture will have a positive deviation from Raoult's law only when delta H of mixing is positive, delta V of mixing is positive, and the attractive force between A and B is always less when compared to AA and DB, and the observed vapor pressure is always more when compared to the vapor pressure which is theoretically expected from Raoult's law. Whereas in another binary liquid mixture shows negative deviation when the attractive force between A and B, two liquids A and B, is more when compared to the attractive force between A and B and B. In case of negative deviation, delta H of mixing is negative, I mean to say exothermic, and delta V of mixing is also negative, and the observed vapor pressure is always less when compared to the vapor pressure which is expected from Raoult's law. Therefore, we have three different types of solutions, ideal solution and non-ideal solutions. In those two types, Ideal solutions are those which obeys Raoult's law at all temperature and concentration, and non-ideal solutions are those which do not obey Raoult's law at all temperature and concentration. Those non-ideal solutions are again of two types. Non-ideal solutions which shows positive deviation from Raoult's law, and non-ideal solutions which shows negative deviation from Raoult's law. Right? So let me start the class at this stage. Okay?